Okay. I'm Caleb Bortey. I'm offering diploma in information technology. I'm in level 200, and I'm in group B. And then I'm a morning student. So I'm here to present. I'm here to present on computer architecture, on based on an assignment given by our lecturer. So first of all, to begin with, why does the data path cycle has a huge impact on the performance of the CPU? So we all know the CPU is the brain of the computer, and it's responsible for executing instruction and performing arithmetic logic operations. The CPU carries out tasks by fetching it from the registers, interpreting it, and executing it. So without much further ado, I'll continue to explain data path cycle. And data path cycle refers to a sequence of operation through which data flows in the CPU. It involves fetching, decoding, and executing instruction. So when the CPU is executing instruction, this is a stage in which the CPU goes through to execute instruction. A high-performing computer system is one of that can perform tasks quickly and efficiently while minimizing the amount of time and resource required to complete the tasks. So there are several factors that can impact the performance of a CPU, but due to time, I'll limit myself to only 4 or 5 probably. So one major factor is the core functionality of the CPU. The CPU primary job is to execute instruction, and the data path is a route that connects all the components involved in the processor, which we have the memory, registers, arithmetic unit, and arithmetic unit. If this cycle is slow or inefficient, every operation the CPU performs becomes slow. So the job of the CPU is to execute instruction. And the data path is a route that connects all the components. So we can use the data bus. A data bus is an electrical path that connects the memory, the CPU to the registers and arithmetic unit to the motherboard. So they work hand in hand, whereby the CPU performs the execution of instruction, which it fetches, decode, and executes an instruction. Secondly, second factor is instruction execution speed. Each instruction executed by the CPU requires a journey through the data path. These include fetching the instruction from the memory, decoding the instruction in the control unit, and then executing in the arithmetic logic unit or similar component. And you have storing the result in the registers. So this process is done by fetching the instruction from the memory. It can be registers because registers is very fast. CPU normally works with registers because it's very fast. Because the RAM is slow when it comes to accessing instruction. So normally the CPU fetches instruction from the registers, and registers are temporary storage area where data are kept to be processed. We have the code, the instruction in the control unit. So the control unit is basically it controls or regulates the flow of communication in the system. Then you have the executor, which executes the instruction. Then it stores it back inside the registers. It fetches the instruction from the registers and later store it again in the registers. If the data path is optimized, these steps happen quickly. A poor design or slow data path means each instruction takes longer, directly reducing CPU performance. And I will talk about the CPU performance, where what affects CPU performance or computer performance is throughput in response time, whereby throughput is the total amount of time a CPU carried out its tasks. Then the response time is the time the feedback gets to the receiver. Yes, it helps. It really helps in the performance of the CPU. We have third on the list. We have bottleneck in pipelining. Modern CPU use pipelining to process multiple instructions simultaneously. For example, the instruction, for example, instruction being executed. So, for example, while one instruction is being executed, another can be fetched and the the tied decoded. However, so what the pipelining simply means is that you see, let's say you have three people doing three jobs. You have three people doing three jobs. So let's say we have worker one, worker two, and worker three. And worker one teaches the student, worker two give student assignment, and then worker three mark the student assignment. So let's say if worker one gives the student assignment, worker worker two must wait. Oh, okay, worker two must mark the assignment, whereby worker three must wait so that worker two should finish giving them the assignment before the worker three will mark. So in that it will take time. So the pipelining does this simultaneously, whereby worker one will give the assignment, worker one will teach, worker two will give the assignment, while worker two is giving the assignment, worker one is what? Teaching again. Then later worker two who gives the assignment give give the assignment to worker three, for worker three to mark, whereby worker two will be giving whereby worker one will give worker two the thing he has taught. Then worker two will give the assignment. It happens simultaneously. So, however, if data part has a bottleneck, which means a slow memory access or connection for resources, it causes pipeline stalls, where the CPU has to wait for one stage to complete before moving forward. This significantly reduces the throughput of the instruction. I explained throughput as a total amount of work that a CPU carries, and then whereby you see if it causes pipeline, so whereby worker one must finish working, so worker two will wait, worker three to wait. It reduces time. It's like it takes it takes a longer period of time before an instruction gets executed. We also have um, interaction with cache and memory. The data part links the CPU with cache and memory. If the connection is slow or inefficient, accessing instruction and data becomes a bottleneck. For example, a slow memory access forces the CPU to wait, delaying execution. So normally, working when the CPU when the CPU is fetching data, it normally fetch the data from the registers, because fetching data from the RAM takes a longer period, which will delay the execution. So the CPU normally goes with the registers. Secondly, if the cache hierarchy L1, L1, L2, L3 is not effectively utilized by the data bus. Performance suffer as the CPU has to rely on slower main memory more frequently. So let's move to question two. And question two, so before we move to question two, let me just bring in the throughput, how the throughput works. So here lies the case, the performance of the CPU and then the execution is directly proportional, whereby the performance of A is inversely proportional to the execution of A. So it works like this. So let's say P performance P of A is equal to 1 over E of A, which means the execution of A. So let's move to question two. Question two, the question says, how does a CPU fetch, decode, and execute instruction? So basically, the CPU fetch, decode, and execute instruction through a process known as instruction cycle. This cycle consists of three main steps, whereby you have the fetch, decode, and instruction. And I will explain it detailed. So let's move to the fetch. The program counter holds the address of the next instruction to be executed. The instruction is then fetched from the memory, RAM, or the registers and loaded into the instruction register. The PC, the program counter, is implemented to point the next instruction. So somebody will be like, what else? Instruction registers. So basically, instruction, instruction registers is instruction registers. So let me see. Um, let's say it's it's normally like it's a component of a register which holds the current data being executed. Yes. So let's say this data is going to be executed. It holds the it holds the current data being executed, whereby the program counter points to the data or instruction being executed. Then we move to the code. So the decode means, let's say, programming. You see, programming, you have to you type in the English language, whereby it's a high level language, and then we have the assembly language. So the decode simply interpret the human language to the machine language, so the machine can understand and execute. So the decode is a process whereby this one is a place whereby processing takes place. So the CPU interprets the fetched instruction. The instruction in the instru instruction register is broken down into opcode, operation code, and operand, data or memory address. The control unit determines the operation to perform and activate the necessary CPU components. The control unit is normally how information or the flow of data in a CPU. So finally, we move to execution. The CPU performs operations specified by the instruction. If it's an arithmetic or logic operation, the ALU processes it. For data movement, the data is transferred between memory and registers. The result is then stored in the appropriate register or memory location. So on this note, I bring my presentation on on the assignment of how how CPU, the execution of CPU, and how the data path cycle affect the performance of the CPU. So in summary, data path cycle is the stages to which uh, the CPU goes through to fetch the code and execute instruction. And then we have factors that impact the performance of the CPU. Whereby we have the core functionality of the CPU, instruction execution speed, bottleneck in pipelining, interaction with cut and memory. We also have the throughput and then the clock speed. Then we also then lastly, how does a CPU fetch the code and execute instruction, whereby the CPU fetch the instruction from the registers, the code. It is a place whereby the processing takes place. Yes, where it interprets the data to where the computer will understand. Finally we have execution, whereby execution takes place, and then it's stored back into the register. Thank you for a lovely and nice presentation. So thank you very much for the presentation, and I hope It's good. Thank you very much.